In this video, we're gonna look at two more problems. One is about writing an equation that models linear relationship described in a context. The other concerns with writing and solving an equation for a dependent variable. So this is our first problem. Juan predicts that manufacturing 10,000 pairs of flip-flops will cost his company $111,200, and manufacturing 15,000 pairs will cost $165,300. You are giving 4 answer choices. First, we need to identify independent and dependent variable in this function. Since the total cost depends on the number of pairs produced, the independent variable x will be the number of pairs, and dependent variable y will be the total cost of production. We are given two ordered pairs, 10,000 and 111,200, and 15,000 and 165,300. So we can find the slope. M is equal to, and we have a fraction, 165,300 minus 111,200 over a difference between 15,000 and 10,000. And the answer will be 10.82. So this is our slope. Now let's plug in the found slope and the x and y values taken from one of the ordered pairs into a point slope formula to find the equation of a manufacturing cost function. We can take the point, for example, 10,000 and 111,200. So y minus 111,200 is equal to 10.82 times the quantity x minus 10,000. When we simplify, we'll get y is equal to 10.82x plus 3,000. And this is our manufacturing cost function. Let's have a look. So the right and the correct answer will be B, y is equal to 3,000 plus 10.82x. Now let's look at another problem in which we also have to solve for one variable. The boiling point of water depends on the altitude at which the water is boiled, and the relationship between the boiling point temperature and the altitude is linear. At sea level, water boils at 100 degrees Celsius, and at the top of Mount Everest, which is 20,029 feet, above the sea level, water boils approximately at 94 degrees Celsius. At what temperature water will boil at the top of the Mount Bonner, whose height is 16,421 feet above the sea level? Round your answer to the nearest tenth, and we are giving a bunch of temperatures. So let us have a look at this problem. Since the relationship between the height or altitude and the boiling point water is linear, we can try to find the slope of the function. First, you need to decide which variable, temperature or height, is independent and which one is dependent. Does the boiling point is changing depending on the height, or height depends on the temperature? Obviously, the independent variable is height, since the boiling point temperature depends on height, on altitude. Therefore, we have two ordered pairs, or 2 points on the linear graph of the function. While knowing 2 points, we can calculate the slope, or the rate of change at which the boiling point temperature changes with changing altitude or height. The points are 0, 100, and 20,929 and 94. Why 0? Because the sea level is considered to be 0 altitude. After we plug in these points into slope formula, we find that the slope is equal to negative 6 over 20,929. Pretty flat slope. In order to get the slope-intercept formula that will allow us to find the unknown variable t, We don't need to look for the value of B, y-intercept, because we are giving this value. It is temperature 100 degrees Celsius at which water boils at the sea level when height or altitude is equal 0. So now we have a formula for calculating the boiling point temperature at any level or any altitude. T is equal to 100 minus 6 over 20,929 H. And by plugging in the value for H equal to 16,321 feet, we can find the temperature T at which water boils at this altitude. T is equal to 100 minus 6 times 16,421 over 20,929. When we simplify that, we'll get approximately, because we have to round to the nearest tenth, 95.3 degrees Celsius. So the correct answer, let's have a look, is C, 95.3 degrees